Today I'm going to be presenting my PhD defense titled In Memory Computing to Accelerate Machine Learning. So before diving into the technical content, let's talk a bit about human evolution. So when we say the words human evolution, one image that might come to mind is the following. But with the rise of artificial intelligence, the image is closer to this one. And this image was actually generated by ChatGPT. In fact, the number of AI users has increased between years 2022 and 2025 up to 34% in the US. And in 2026, it's anticipated to reach 127 million users. And when the number of users increases, this drives the industry to deliver higher performance. And when we have higher performance, this in turn attracts more users. So it's sort of a positive feedback loop, okay? So in order to increase the performance, usually what people do is that they try to increase the model parameter size, okay, because this gives us more performance. So the purple curve shows us the number of model parameters for different models across the years. And the blue line shows us the memory capacity of the hardware which is currently serving the AI users. And as we can see, there is certainly a gap in between the two curves, and this gap is what we define as the memory wall problem. Okay, so this is one side of the story. Now the other side of the story is when the number of users increases, we need to increase the infrastructure that is able to serve those people. And we have seen that the number of AI servers has been increasing, and in 2027, it's anticipated that around 45% of the general purpose servers will actually be AI servers. Okay, and when we talk about data centers and AI servers, we have to talk about energy. So quoting Bill Gates, as AI gets more sophisticated, the energy required to run these models is going to skyrocket. We have to find greener ways to power data centers. Quoting Elon Musk, AI is the biggest consumer of electricity that no one's talking about yet. Data centers are going to be the new oil fields. And finally, quoting Sam Altman, training GPT-4 cost more than $100 million and consumed a shocking amount of electricity. The next generation will need vastly more. Energy is a fundamental bottleneck. In fact, if we look at a study that was done in 2022, we see that the electricity consumed by data centers is bigger than the electricity consumed in entire countries. And as a recent study done by Berkeley Labs shows that by 2028, the amount of electricity consumed by data centers, AI data centers, is going to be 12% of the total electricity in the US. So obviously there is a sustainability problem. So up till now we have defined two problems, the sustainability problem and the memory wall problem. But if we look at the current prevalent hardware architectures inside the data centers of today, they are usually either CPUs, GPUs, ASICs, or a combination of all three. And if there is one thing which is common in between all three architectures, it's their underlying architecture, which is called the von Neumann architecture. So in the von Neumann architecture, the processing unit is physically separated from the memory units, and especially the main memory and other faster memories like caches. And the problem is with this architecture, the buses are the problem. So there is a lot of trips of the data back and forth between main memory and processing units. So this architecture suffers from the memory wall problem and the sustainability problem. Maybe we can mute.
Can you mute?
Yeah, thank you. All right, so that being said, our proposed hardware solution is to shift into a data-centric paradigm, and that data-centric paradigm is in-memory computing. So in in-memory computing, we propose to do part of the computation inside the memory array itself. So of course we still are connected to main memory, but in this paradigm we hope to reduce the number of trips between main memory and our processing unit, hence reducing the memory wall problem and having a more sustainable design. Okay. What happened? Okay. Okay, so the problems discussed so far are the memory wall problem and the sustainability problem. And I spoke about the hardware perspective of things, but now looking at the software side, there is a popular technique in literature that is used to reduce the memory footprint, and that technique basically reduces the size of the data, hence the size of the data going back and forth between the processing unit and the main memory is reduced, and hence it would take less energy to do those transfers. And this technique is called quantization. So in quantization, we would have continuous full precision value ranges, and each range will be mapped into a quantized discrete value. So this is what quantization does. So it's essentially a mapping. And when we talk about quantization, we have to realize that there is a trade-off between accuracy and savings, because when we quantize data, we are losing some information, and it really depends on how extreme we're quantizing. So if we're choosing to quantize data into a higher precision, then we are favoring accuracy over savings. Otherwise, if we are choosing to quantize data in a lower precision, then we are favoring savings over accuracy. To strike a better balance between accuracy and savings, people in literature have been looking at what's called mixed precision quantization. And in mixed precision quantization, we allocate different precisions to weights and or activations across the model. Okay? And again, if we look at the current hardware in data centers, the problem is in their processing units, the registers are of fixed or constant width. So really they cannot support the computation of mixed precision in its real form. What they do is they usually unquantize the values and perform the operation in the size of the register. Otherwise they pad values with zeros, and they also conduct the operation in the register size. So they're not really squeezing performance out of the mixed precision computation. So we already, so there is actually a flexibility problem. This is what we call the flexibility problem in the current hardware architectures. So to tackle the memory wall problem and sustainability problem, we have proposed in memory computing. But to tackle performing mixed precision computation, we specifically focus on the associative processor, which is one form of in-memory computing. So it performs massively parallel search and arithmetic and logical operations. And the way it does so is by following a series of compare and write according to the lookup table of the associated operation. So I'm going to show an example later on that clarifies this. But this is what the associative processor looks like. So at the heart of it is a content addressable memory, which has a bunch of content addressable memory cells. Each cell stores a bit. It could be either SRAM based or ReRAM based. And then there is a key register that presents the data to be searched across the CAM. There is a mask register that indicates which bits are activated during the search and write operations. And there is a tag register, which indicates the matched rows after we perform a search operation. So to better clarify the functionality of the AP, let's assume we're doing a simple operation, which is the XOR operation. So assume we have two vectors, A and B, and each vector has 4 elements, and each element is of precision 2. And the goal is to perform A XOR B. So this is our CAM over here, and we store A and B in our columns, and we reserve columns for the result, which we will save later on. So basically, in order to perform the XOR operation, we have to follow the lookup table of the XOR operation. And we have similarly lookup tables to every other arithmetic or logical operation that we want to do. But for the XORs, the first step we do is, first of all, we select the least significant bits of A and B. And the way we do it is by the help of the mask. So the mask helps us to select these 2 columns. And we start following the lookup table. The first compare pass will tell us to compare 0, 1 to the entries in the lookup table, and we see that the last row matches, so we assert its tag. So in the next subsequent cycle, what we will do is we will write a value of 1 in the least significant bit of the result of the row which matched in the previous compare cycle. So this is going to be the last row. And then we follow the lookup table. So we go to the second pass, we search for 1, 0 in the key register. This will match with the second row in the lookup in the CAM, and then we assert its tag value. So in the next cycle, we have to write a 1 in its result. Okay, as we can see over here. Now that we have done, we are done with the lookup table passes. As we can see, the next thing we do is we move to the next bit next to the least significant bit. In this case, because we only have 2 bits, is going to be the most significant bit. So we select the most significant bits of A and B, And we repeat the process. So in the first pass, searching for 0, 1, the first row matches, we assert it, we write 1 in the most significant bit of its result. And in the second pass, we're searching for 1, 0, we can't find that entry in the CAM, so we can simply skip the subsequent write operation because we won't be writing anything. So actually, what we see in the result columns is the final result, so this is actually what we get. And if we look closely, actually the result column is storing the XOR operation of A and B. Now I want to note that the energy and latency of performing operations in the AP scales at least linearly with the precision because of the way it operates in a bit serial word parallel manner. But in some, we say at least linearly because in some cases it scales quadratically, for example, in multiplication. Okay, so that being said, we mentioned that APs are a good fit to perform mixed precision quantization or computation, and the reason is its bit fluidity. So bit fluidity, we define it as the ability to support mixed precision. So again, an operation in the AP is performed bit serially from the least significant bit to the most significant bit. And if we take another example where we're storing two vectors A and B and we're trying to perform the in-place addition A plus B and to write it back in B, the mask register will tell us where to start the operation and where to end the operation. So in this case, we can see that we are skipping the first two columns of A and the first column in B. So this ability to control where we start and end the computation is why the AP is inherently able to support mixed precision by simply changing the start and end position of the computation. Okay, so that being said, the research objective of my PhD becomes the following. So I'm trying to make sure this equation is a viable equation. APs can provide acceleration by solving the memory wall problem, sustainability by being energy efficient, and flexibility by supporting mixed precision computation. And if we want to word this in a more formal general way, so the research objective is actually to promote the use of in-memory computing to accelerate machine learning. So this is in terms of research objective. Now, in terms of research contributions, we've been promoting APs for accelerating hyperdimensional reinforcement learning, which resulted in a first author publication in ACM Journal or Emerging Technologies in Computing Systems. We've surveyed mixed precision neural network frameworks, which resulted in a first author publication in IEEE Transactions on Pattern Analysis and Machine Intelligence. And we've promoted APs for mixed precision convolutional neural network acceleration, which resulted in a first author work currently under review in IEEE Transactions on Emerging Topics in Computing. And we've promoted APs for mixed precision large language models acceleration, which resulted in a first author publication in the 2025 Design, Automation and Test in Europe Conference and Exhibition known as DATE. Okay, so now I'm gonna be focusing on these three works because of the sake of time, but I'm going to briefly go over our first work as I've already gone over it in the qualification presentation. So the first framework is HDR-LPIM, a simulator for hyperdimensional reinforcement learning based on processing in memory. And just a quick background on hyperdimensional computing-based reinforcement learning. This is what the paradigm looks like. So we have discrete states that are encoded into high-dimensional vectors known as hyperdimensional vectors. And we have a random initializer which initializes a policy. And then we multiply the hyperdimensional vectors with the policy to get the Q matrix. We select the maximum Q value out of the Q matrix and we select its associated action. We apply it to an environment, and then this action, in addition to a new state which is generated by the environment, is stored in the replay buffer, which is then used to sample and replay or to find another maximum Q value and select the next action and apply it. And our focus in this framework was on accelerating these two steps, so the multiplication step and finding the maximum Q. The reason is we focus on the multiplication step because it's computationally heavy, because the D dimension is very big, because it's a hyperdimensional vector, and we focus also on accelerating the finding the maximum Q value because it comprises a search operation which APs are very good at because of the content addressable memory. So that being said, the proposed framework is then HDR-LPIM. And this is what it looks like. So assume there is a hyperdimensional reinforcement learning application running, and we collect traces about the sizes of the matrices, how many times we perform the multiplication during the inference process. And then we have a simulator of the AP that offline takes those traces and estimates the energy, latency, and area of performing those operations on the AP. Now the details of how we model analytically the energy, latency, and area will be clearer as we introduce the CNN work later on, because it's a bit similar. But for the sake of time, this is what the framework in general looks like. And if we look at some of the results we got, so over here we have the energy delay product versus the dimension. So this is the D, we're varying it, and then the bit width, so the precision. And the energy delay product, lower is better. And we plot against the baseline implementation, which is an FPGA implementation. We have an SRAM-based AP and an RRAM-based AP, and we have two workloads, cart pole and lunar lander. And in both cases, and for all possible combinations, we can see that the energy delay product of the AP implementation is way lower than the FPGA. In fact, the SRAM-based AP implementation shows up to 1,000 times EDP gains compared to the FPGA counterpart. Okay, so we hope that this work has promoted the use of hyperdimensional reinforcement learning with APs. And next, we're going to be looking at the next work, which is a review of state-of-the-art mixed precision neural network frameworks. And we mentioned before that mixed precision means allocating different precisions for weights and or activations across the model, but there are different levels of granularities at which we can do that. There's a tensor level, channel level, and layer level. And as we go up, down the hierarchy, we go finer in the granularity. So the tensor level is the finest granularity, but of course the complexity of the optimization algorithm increases because of the granularity. And then if we go up, we have less flexibility. Flexibility meaning that we don't really have a lot of control for the trade-off between accuracy and savings when we are at the layer level compared to the tensor level. Okay, but we have seen that when we surveyed the works in literature, because it's less complex, most of the works are doing layer level mixed precision. So each layer in the neural network model has a precision for weights and or activations. Okay, so in fact, we have surveyed at least 25 works in literature, and we have categorized them according to their optimization technique, and we identify 4 main optimization techniques for mixed precision allocation. The first one is gradient-based, where it allocates the mixed precision of bit width by constructing an optimization problem and solving it via a variant of gradient descent or an approximation of it. The reinforcement learning-based optimization, which allocates the mixed precision by formulating the optimization problem as a reinforcement learning or a deep reinforcement learning problem and solving it by maximizing some reward. And the heuristic-based optimization, which allocates mixed precision by constructing and solving an optimization problem that computes a heuristic assessing the sensitivity of the layers. And finally, the meta-heuristic-based optimization, which performs mixed precision allocation of bit width by constructing an optimization problem solved via differential search or evolutionary search algorithms. So the paper has more details on the exact workarounds of these optimization algorithms, but what we do is we summarize these frameworks and their performance, and I just want you to, for the sake of this presentation, to focus on these 3 columns that we define as metrics, whether they are there or not in each framework. The first one is hardware awareness. By hardware awareness, we mean whether the framework is taking the hardware parameters in the loop while performing the mixed precision optimization. By automatic allocation, we mean that the framework is not relying on a brute force approach. And by runtime configurability, we mean whether the framework is capable on the software side to support a dynamic need to change the mixed precision at runtime. And as we can see from these frameworks, some of them have hardware awareness, some of them don't. All of them have automatic allocation, but none of them have runtime configurability. And the same applies to these frameworks, except for BitMixer over here, which claims to support runtime configurability from the software side, but I just want to note that they do not mention anything about the hardware implementation of such a mixed precision dynamic support. Okay, so we define
Mariam,
actually...
can you go back to the
Yeah.
slide? Go back one more.
This?
36. Can you, you've done this nice survey. Can you give us some insight as to, if I were to try and deploy these type of techniques, what kinds of approaches might be suitable for low power edge devices versus large scale data centers versus mobile versus blah 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 blah. So can you give us, because you've done a nice survey, but it'd be nice if you could say a few words about the applicability of these different types for different domains.
Okay, I'm gonna show this extra slide that I had here. It's a hidden slide, but actually when we compared the frameworks, because we wanted to see, okay, which technique is relevant or better, it really depends on what we care about. Do we care more about accuracy, more about the compression rate? So if we're targeting edge devices, we're probably going to care a bit less about accuracy and more about the compression rate. And it seems to us from this...
Well, it would depend on the application.
Yeah.
Right? If I have an edge device that's life critical, then maybe accuracy is important. And so, a little bit. But you're right, keep going.
Yeah, so that makes sense. Actually, if it's a critical, if it has a critical importance, then we have to look more on the accuracy. But in general, all of the framework techniques, they fall in a similar bag over here, where they strike a bit of a balance. But we have seen, so this is just showing top 1% accuracy versus compression rate, but it's not showing how much time the optimization technique is taking. Usually the heuristic-based approach, so this is the approach, the frameworks which are in the red circles. So these ones, they take the least amount of time, and the reason is they rely usually on a sensitivity-based metric. So let's say on the Hessian trace, they approximate the Hessian trace, and then they can, according to the sensitivity of the layer, they assign different sensitivities. For different frameworks like reinforcement learning, for example, then it becomes a bit more expensive because there is an agent involved in the process of the mixed precision. So in terms of which one takes less time, optimization-wise, it's the heuristic-based, but in terms of performance, it really depends on what we really care about, but most of them are lying here in the middle, most of the frameworks. This is what we've seen.
And is there a sort of a direct correlation to energy usage as well here, or is that counterintuitive? Because it's not clear from here.
Okay, so this is a good question, but actually most of these frameworks, they look at things from the software side only, except the ones which take the hardware awareness into consideration. So not a lot of them report energy. Actually, if we look at the table, let's see. Yeah, I'm just over here showing savings and top 1% accuracy, but in my original table when I was writing the paper, I had an energy column, but it was mostly empty. Only like 2 or 3 works mention anything about energy. But this is a good point. Usually, I think in their case, they're just trying to say it depends really on the compression. The more compression we do, probably this would yield to more energy savings. Logically, but there are no numbers in these frameworks given, which actually brings us to the future research directions. So we identify in the survey a couple of future research directions, whether it's on the software side or on the hardware side. But on the software side, we actually call for more hardware awareness because this is an important issue. So there was only like a couple of works, HAQ is one of them, that they just take the hardware performance into the loop. And those frameworks do report the energy savings in this case. But more hardware awareness needs to be there when looking at mixed precision quantization. Also more runtime reconfigurability, because in a real system, the needs of the system might change over time, and we might need to change the precision, the mixed precision configuration over time, which is something that only one work has looked up on, at least from the works we've surveyed. From the hardware side, we obviously need to look at hardware that supports bit fluidity, and this is what we are trying to do what I tried to do in this PhD. So actually we can define a precision allocation matrix which has 4 quadrants: static fixed, static mixed, dynamic fixed, and dynamic mixed. When we say static and dynamic, this relates whether we can change the precision at runtime or not. And by fixed and mixed, we just mean whether the quantization is a mixed precision quantization or a fixed precision quantization. Again, a fixed precision quantization, all weights in the model have the same precision. It's just quantized to a lower precision all over. And as you might have guessed, the AP can do all four, and this is mainly the dynamic mixed one, which is interesting to us. That is why we have been looking at it, and this survey has motivated us to look into the next framework, which is BFMNA. So this is a bit fluid in memory neural architecture for neural network acceleration. So we're trying to do end-to-end acceleration of CNNs using mixed precision with APs. Okay, so just a quick background on CNNs. So we have an input, which is a matrix. We have a bunch of convolutions, which we will see later can be translated into matrix-matrix multiplications. And we have pooling layers, whose purpose is to reduce the dimensionality of the output from the convolution layers. And this is called feature extraction. And then we go through the classification process by flattening the output in the fully connected layers, and finally classifying. Okay. So usually people in literature see convolution as a general matrix multiplication. So the technique I'm going to go over now is called M2col. So this is image to column. And it is only one technique that people use to translate convolution into a matrix-matrix multiplication. So assume we have a 2 by 2 by 2 input. So this is in orange, and 2 by 2 by 2 by 2 filter over here. And we want to translate this convolution into a matrix-matrix multiplication. And it's pretty simple. For the weights, we just flatten each channel. So W1 to W4 is flattened, and then the same for the other channel, and the same for the other kernels. Now for the input, to flatten it into a matrix, we assume that the actual weight is a sliding window on the input. So actually, first of all, the weight would be a sliding window on the first 4 elements, and we flatten those, I1 to I6. Then we move the sliding window. In this case, we're assuming a stride of 1 by 1, and we flatten it, and we keep doing so until we flatten the last element, and we do the same for the other channel of the input. And this is how we come up with this matrix-matrix multiplication. So in reality, this convolution is equivalent to performing the matrix-matrix multiplication, and the output we get from the matrix multiplication, if we unflatten it, is nothing but the output of the convolution. Okay. Now for the proposed architecture, it's called BFMNA, and this is what it looks like. I want you to focus on the red square over here. This is our chip, and then we have a bunch of clusters on the chip, and these clusters are connected to main memory via an off-chip interconnect, and each cluster has a bunch of computational APs called caps, and one memory AP called a map. And what we want to do eventually is to store all the weights needed for computation in the map. And then while we're doing the end-to-end inference, we stream those weights from the map to the caps via the on-chip mesh. And now each cap is an AP, but instead of just using a regular AP, we're actually using a 2-dimensional AP. So I've talked a bit about APs. This was the 1-dimensional AP. So the 2-dimensional AP just has extra peripherals to perform operations in between each pair of rows at a time, which is good for reduction in place. So we mentioned before that the functionality of the AP is a bit serial word parallel functionality. And if we really look at convolution as a matrix-matrix multiplication, a matrix-matrix multiplication has 2 main operations, a multiplication and a reduction. So the multiplication will be done between the columns, like we've seen, similar to the XOR operation. So the output will be in the different rows of the AP. Now we would want to perform the reduction in between the rows so that we do not move the data a lot. We can do it in place by relying on the 2D AP, which has extra peripherals that can select 2 rows at a time, reduce according to the lookup table. Okay, so this is what we use for this architecture.
Mariam, is the on-chip mesh, is that just nearest neighbor grid connections?
Yeah, so this one is just a bus. It's just like a bus. Okay, we're calling it a mesh just because of how it looks like, but it's really just a bus.
Bus meaning only one transaction at any time?
We are going, it has a certain width, but yes, and we do not use neighbor to neighbor because we don't really need to transfer data from one cap to the other. We need just to transfer weights from the map. Mm-hmm. So from a central unit, which is the map to all caps. So it's a bus with broadcast. This is what.
So broadcast.
But we do not need really to communicate in between the caps themselves. And then after we perform the computation, the result will be then written from the cap to the map. So it's always inwards or outwards to the map and from the map. Okay, so this is the pattern that we need. That's why we
But
just
on the writing, so one-to-many is a bus, but how do you do cap to map simultaneously? Or is that done over multiple cycles?
So this is done over multiple cycles. It really depends on the size and whether we can. So usually, as we will see later on from the mapping that I will show, we have the different outputs, and the number of outputs is way lesser than the number of inputs. So it depends on the size of the outputs. If we can transfer them in parallel through the width of the bus, we do that. Otherwise, it's like recurring transactions. It depends on the size.
Is that done by a compiler, or who does the scheduling of all of this?
Okay, so in our case, this is a good question, but we are looking at things, so we model this from an analytical perspective. So we model it analytically and we hide latency mathematically, but in reality, there should be some scheduler that's doing
Okay.
so.
So you've just done kind of a conceptual design?
Yes, so usually it's done through this controller, like inside the AP. But for purposes of our modeling, we do not model that specific component. Okay, so I had also a question on Zoom on how do I do in parallel between rows. So we do each pair of rows at a time. So it's similar of when we select the least significant bits, 2 least significant bits, and perform the operation according to the lookup table. Very similarly, we select 2 rows and we perform the operation by following the lookup table. So it's just like the other dimension.
So maybe I think perhaps the 2D AP has horizontal and vertical keys, so you can do
Yes.
the search, compare, and write in 2 dimensions at different times, not at the same time.
Yeah, exactly. So there are extra, actually here, mask and key registers that are able to do that, so that they do not interfere with the mask and register that are up there.
Makes sense.
Okay. Okay, so now for our analytical modeling. So as I mentioned, we're just doing an analytical modeling of performing the end-to-end CNN acceleration, but we model each phase of the CNN inference as an operation, and as we've seen, convolution can be represented as a matrix-matrix multiplication. Usually it's followed by a nonlinear operator. In this case, we focus on ReLU. And the fully connected layers is also nothing but a matrix-matrix multiplication. So we model the runtime and the energy of performing such operations on the AP. And we also model performing the pooling, whether it's max pooling or average pooling on the AP as well. I just want to note that for pooling, there were no lookup tables there in literature, so we had to come up with our own lookup tables to perform max pooling and average pooling. Okay. So just to put this mapping in sense a bit, so let's, for example, assume that we are trying to map so this is what the scheduler will do, but we're just explaining it on how it's done. So we have the matrix-matrix multiplication and we want to perform it on the AP. For sake of simplicity, let's assume we just have 2 clusters, cluster 1 and cluster 2, and we just have 2 caps per cluster. And for now, assume that, just focus on the first column because different columns are different time steps. Okay, so the first step we have to do is remember our weights are already stored in the map because this is a premise of our work. So weights are stored in the map. So first of all, we read those weights from the map and we transfer them to the caps. And then we stream the inputs, the associated inputs from off-chip memory. And then this is the first stage of the computation, basically. Next, we actually perform the computation whereby we find the outputs of the matrix-matrix multiplication by following the lookup tables. And after we have the outputs stored inside the caps, we finally transfer them from the caps to the map because they will serve as inputs for the next layers. Okay, so we keep repeating those 3 stages across time steps until we finish the whole computation. I just want to mention over here that we have 3 degrees of parallelism in our architecture. The first of one is the number of clusters because clusters are operating in parallel. The second one is the number of caps per cluster because caps are operating in parallel in each cluster. And the third one is the number of rows in the AP because we're doing things in a bit serial or parallel manner. Okay, so this is for the mapping. Then for our architectural choices, we thought about two things. First of all, we thought, okay, if we can fit all the weights on chip in the map, can we perform all the computations simultaneously, at least per layer, because the next subsequent layer will depend on the previous layer, so we can do all layers simultaneously. But for this approach, we assume we have infinite computational resources to perform everything in parallel. So this is when we have maximum throughput. Like according to our analysis, obviously this approach is not realistic because we will end up with a very big area. So we thought about a more rational approach, which is having limited computational resources. So now we have limited computational resources, so we have a big problem, we tile it and we map it to the smaller hardware, so we have time folding involved over here. And for the limited computational resources approach, these are the specs of the hardware that we take into consideration. I just want to mention over here that this area is taking into consideration the map area necessary to store all the weights of the biggest model, which is in our case VGG16. Okay, and this is SRAM-based implementation, because I'm going to show in the results we try ReRAM and SRAM, but this is for the SRAM-based implementation. For our experimental setup, so for the analytical models I previously showed you, we used a micro benchmark consisting of random vectors and matrices to validate the proposed mathematical models. And for the BFMNA architecture itself, we developed a Python-based AP simulator for BFMNA. We modeled SRAM and ReRAM-based APs in 16 nanometer technologies. And we simulated the end-to-end inference execution on BFMNA according to the data flow that I've showed before. And I just want to mention that the energy numbers that we rely on in our modeling are also our work, which was previously published in TCAS 2, and this work is based on, it accurately models a CAM in SPICE, so it's based on accurate SPICE simulations. Okay, so for our results, first of all, technology, ReRAM versus SRAM. So we performed an end-to-end inference of VGG16 on our limited resources approach, and then we plot over here the ratio of ReRAM to SRAM energy and ReRAM to SRAM latency versus precision. And the energy is in purple and latency is in green. And the first thing we notice is the ratios are always bigger than 1. This means SRAM is always better than ReRAM technology in terms of energy and latency. And this makes sense because the SRAM cells require A, 4 orders of magnitude less energy, and B, half the cycles to write compared to ReRAM cells. The other thing I want you to notice is the trend. So as we increase the precision for the energy, the gap between the two technologies is reducing. And the reason is as we increase the precision, the bit serial because of the bit serial operation, the compare energy becomes more dominant than the write energy in a sense. And the compare energy in both technologies is the same. That's why this gap reduces as we increase the precision. Now, if we look at the latency, the trend doesn't change a lot or not at all. And the reason is, as we will see later on, for latency, if we look at the bottleneck of latency, it's going to be the reduction operation, not the multiplication operation. And the reduction operation is done between rows, so it doesn't really depend on the precision. That's why as we change the precision, the latency doesn't really change a lot. Okay, so this is, okay, so SRAM seems better than ReRAM and everything. Why did we even look at ReRAM? Well, because ReRAM offers 4.4 times area reduction because of its density. But because area is not the focus of our work, it's not our concern, because our area wasn't too big, even fitting all the weights on chip for VGG16. That's why in the rest of the slides we are going to be relying on the SRAM technology, especially that it's more reliable and it does not cause issues when we write a lot. Okay, so now we're showing the energy per inference versus precision for 3 models, VGG16, ResNet50, and AlexNet, for the 2 architectural choices. IR, which is infinite resources, and LR, which is limited resources. Infinite resources are circles, limited resources are squares. And I just want to note that for the precision over here, we see some precisions which are like decimal values. This is because we are mimicking having a mixed precision mapping whereby the average precision is, let's say, 2.5. So we have a configuration of mixed precision, and then if we add it and divided by the total number of layers, we get this precision over here. So this is
did you say the squares are limited precision and circles are infinite precision?
yes.
So can you explain why in the green sets the infinite precision is doing is consuming more energy, but in the other two it's inverted?
Okay.
So there's something.
Yeah. So over here the
Right?
energy
The
is
circles are below the squares in
Yeah.
the bottom two. So what's
okay. Good. So actually in energy the square and circle is almost the same energy-wise, because energy-wise we're still doing the computation. Okay. The only difference is whether we transfer them all at once and do them, or we time-fold. So it's gonna be shown in the latency where this difference comes into play. Now the small differences are because of the communication in between. So we haven't looked at exactly why this behavior is exhibited, because the changes are very, very minimal, like between the two. So they're almost the same.
Well, it's on a log scale, right?
Yeah,
So,
but it's really, I mean, when we look at the values, it's 0.00. So the difference is because of the communication pattern, but we have not looked at why. This is what this is showing. So actually the thing that dominates energy is the gem operation, while the communication pattern is less than 1%. And the communication pattern is what's different between the two, and this causes the small discrepancies between the two designs. But mainly I wanted to note like two things, that the green curve is higher than the orange, which is higher than the blue, because VGG16 has the highest number of parameters, so the most number of computations, and then the lowest one is AlexNet, which has the lowest number of parameters, so the lowest number of computations. And then as we increase the precision from 2 to 8, we have a severe increase in energy because of the bit serial word parallel operation. So again, the AP does best at the lowest precision, which is 2. For latency, so now the difference becomes very huge between the limited resources approach and the infinite resources approach, because obviously of the maximum throughput versus not. So this is one thing we want to know. The other thing is, if we increase the precision from 2 to 8, the latency across the models is changing, because this is log scale, but not a lot, not as much as energy, because again I mentioned that reduction is the dominant operation in the gem, and this depends on the number of rows and not the number of columns. What gets affected by the precision is the multiplication, which is not dominant for purposes of latency. So this is why we see this trend for latency when we increase the precision.
Can you give me the intuition for why the limited precision and the full precision energy numbers are similar? Because intuition might say that I need to do with limited resources.
Mm-hmm.
If I have limited resources, then maybe I have to reuse those resources through multiple cycles to do the same computation.
Correct.
Which might mean I need to consume more energy. The intuition says that, right? But it seems like if you go back to the previous picture, they were kind of, maybe you can argue whether it's more or less, but it seemed to be clustered together. So
Yes.
am I missing something?
So again, because the computation itself, whether we have enough hardware to do it, like whether we have a very big chip and we're doing the computation all in parallel, or we have a smaller chip and we're folding in time, the only difference is the communication pattern, but the computation part itself is still the same. We're doing the same amount of computation regardless of the size of, it's just whether we're folding it in time or not.
It's probably your wire length.
Mm-hmm.
Yeah, so it's the communication over here which is the different, which will yield some differences in energy, but because it's not a lot of energy compared to the gem, that's why the differences are not shown in between the two
I think
approaches.
the buses are bigger in the infinite precision.
Yes, I mean we assume that we can transfer everything all at once, so we can do like all the computation all at once. But yes, it is the communication that's the reason, and it's not a big chunk of the energy, that's why it doesn't show a lot.
And you're not explicitly multiplexing things like we normally do is you're just transferring data piecemeal as opposed to transferring large amounts of data in one sense. So my guess is this is probably maybe, but it's a good question to follow up.
Yeah, this is a good question. Yeah.
Mariam,
Yeah.
can I ask? Can you hear me? Can I ask one question
Yeah.
as
Yeah.
well?
We can hear you. Yeah.
Okay, good. My question actually is, you said in the beginning, if I got that right, that this is an analytical model. You're not really simulating it like you
Yes.
would do in System C with
Yes. Yes.
steps and with structure and with components and so on. Is that right?
Yes, this is right. So what we do is we take each layer in the CNN model, and then layer by layer we map it to our hardware, because for each layer we know the sizes of the matrices, so we can estimate how much time and energy it would take to compute this layer, and then subsequently we take the next layer and so on and so forth.
Okay, so you're looking at matrix sizes
Yes.
and number of bits and these kind of parameters, but you don't really have an understanding of a bus cycle or a scheduler like was
Yes.
mentioned before and things like that, right?
Yes, so it's just an analytical model, this is true. We take into consideration just the sizes of the matrices, and then the sizes of data that needs to be transferred over the bus, and we check if there is some latency hiding or not. Like we can be transferring some data while we're doing part of the computation and things like that. But on the analytical model level, there is no, it's not like Gem 5 or System C. Yeah.
But when you're talking about the bus structure, before there was a mesh network came up and things like that, do you know this structure, how that looks like, or do you simply have assumptions like on a bus, one transaction happens at a time and you simply sum them up to get some delay or
Yes,
some
yes. So
latency?
I assume there is one bus which supports broadcast, and then it has a certain bandwidth and a certain width, and because I know the amount of data that I want to send over the bus, I just estimate the energy needed and the latency needed to do the transfer. There is no, well, how do we schedule the transactions, and is there like some waiting and buffering and things like that? So we do not model at that level. That's true. So it's a very simplistic model of the communication.
We call it high level, don't call it simplistic. That would be better. But anyhow, did you attempt or think about, or is this future work, to compare this to a couple of specific examples at lower levels of abstraction, to see whether your modeling is actually accurate, or whether you get somehow get the same lessons learned? The lessons learned out of your model need to be the same as what lower level models need to show. Is that right?
Yes, so even though this was a high level model, so currently what we're working on, as I will just mention briefly later on, that we're working on accelerating end-to-end LLMs. So for that work, we came up with a C++ simulator, and we're integrating it with like tools like Cacti and BookSim, which are able to simulate an actual on-chip interconnect.
Thank you. Thank you very much. I don't want to delay this any further. We are already getting over time quickly. Thank you.
Yeah, sure. Okay, so just a small comparison with the state of the art. So these are peak numbers, and I'm showing here GOPS, which is throughput, GOPS per watt, which is energy efficiency. Higher is better for both. And if we look at the framework that has the highest throughput, it's going to be the H100. And if we compute its energy area efficiency, is going to be 3 GOPS per watt per millimeter square. And if we look and it performs the inference at a precision of 8. So these are all works that perform fixed precision. So for that purpose, we're comparing to a fixed precision implementation as well for our technique. So at a precision of 8, our energy area efficiency is 8 GOPS per watt per millimeter square. So it's 2.7 times better than the H100, and this means we can solve a larger chunk of the problem on using the same area, because we are fitting things on chip. Okay, so this is for throughput. Now, if we look at the SOTA work in literature that has the highest energy efficiency, it's going to be this one. Compared to it at the same precision, yes, we have 38 times lower energy efficiency, but we are 149 times better in throughput. And then if we look at these three state-of-the-art works, so these ones, they perform the inference in a precision of 16, and at a precision of 16, our framework really loses its advantage because this is a very high precision because of the bit serial word parallel manner. But still, even at 16, the precision of 16, we achieve 1.02 times higher throughput compared to Isaac, while having 3.66 times lower energy efficiency, and compared to PyPlayer, we have 2.95 times lower throughput, while having 1.19 times higher energy efficiency. So the conclusion is, like BFMNAC can perform comparably well to other state-of-the-art works, but what's interesting is none of these works can support mixed precision, while BFMNAC can. So to demonstrate the bit fluidity, we actually go and implement mixed precision inference on ResNet 18 based on HAWK v3. So HAWK v3 is one work that I've surveyed in the survey. So these configurations for precision are taken from that work and also their associated accuracies, and we anticipate the accuracy in our case won't change because we're using digital compute. I want to point out a couple of things. First of all, if we look at the configuration where all 19 layers have a precision of 4, so this is fixed int 4 quantization, we have the best EDP because it's the lowest and the worst top 1% accuracy, versus if we look at the implementation which has all int 8 fixed precision quantization, then it has the best accuracy versus the worst EDP. And this makes sense because this is int 4 and this is int 8. Now, if we look at the mixed precision implementations, our estimations tell us that yes, mixed precision quantization does hit a sweet spot between EDP and top 1% accuracy because the numbers come in between. Okay. Okay, so hopefully in that work we have been able to promote APs a bit for CNN inference with mixed precision. Next, I'm gonna finally talk about this final work, which is SoftMap, software hardware co-design for integer-only softmax on associative processors. And since we're talking about softmax in LLMs, I'm just gonna go a bit about, with a background on transformers. So the transformer block looks as follows, and we're usually given n tokens, and our goal is to predict the next token. So these n tokens, they get divided onto h heads, and each head operates in parallel, like all heads operate in parallel. And for each head, the portion of the tokens given to that head go through linear layers of pre-trained weights to get the query key and value. Then QKT gets performed, so this is a matrix-matrix multiplication. Softmax gets applied to this matrix-matrix multiplication elements, and then we multiply the outcome of the softmax by V. And then the output from the different heads are concatenated, passed through a linear layer, and finally through a feed-forward network. I just want to note over here that softmax in transformers, especially in attention, is very computationally expensive because of the way it's computed. So mainly for every sequence length element in the n tokens, we have to find the exponential. We have to sum across all sequence length elements. We have to do this for every token, so n times. So this is very computationally expensive. In fact, our characterization reveals that for Llama 2 7 billion, the softmax runtime percentage compared to the end-to-end inference of Llama 2 7 billion reaches up to 38% at a higher sequence length. So really, softmax in attention is a major bottleneck. And works in literature focus on quantizing matrix multiplication operations, but the existing quantization methods, they struggle to quantize softmax due to its sensitivity. So the solution is to come up with an efficient softmax quantization and acceleration framework, and this is where SoftMap comes into play. So SoftMap is a software hardware co-design, where on the software side, we propose a softmax approximation and perform a precision sensitivity analysis. And on the hardware side, we propose the AP as the efficient custom hardware, which can inherently support mixed precision to accelerate the softmax kernel. So from the software side, we rely on an integer-only softmax approximation. So we are using second-order polynomials to approximate softmax. And the point is, at each step of the approximation, we would want to vary the precision of the variables used, and then eventually perform some precision sensitivity analysis to check how the mix of precisions affects the end-to-end performance of the model. And on the hardware side, our role is to map each step in the approximation to the AP, estimates its energy and latency to be able to come up with a total estimate of how much energy and time the mixed precision softmax kernel will need. And from the hardware perspective, just for an example, if we just focus on these two steps, 1 and 2, the ones in yellow, the way we do it is, again, we just translate those into the AP. So if we have writing V and max of V is a vector in this case. So we write the elements in the different columns. I just want to note over here that the number of rows is the sequence length. So this is going to be important later on for sake of explaining, but we replicate the maximum of V in B, and then to perform the subtraction, we mimic performing it on the AP by relying on the lookup table of the subtraction, just as we shown for XOR. So we're going to show it like this in the next slide. So we're going to, similar to these two steps, we map all subsequent steps onto the AP step by step, estimating the total energy and latency of performing the softmax kernel on the AP. Okay, for our experimental setup for precision sensitivity analysis, we integrate the approximated softmax in the Llama 2 family of models. We evaluate the end-to-end perplexity on Wikitext2, and we use 2048 token context, and we ran our experiments on NVIDIA GPUs 3090 and A100. For our hardware modeling of the AP, we developed a Python-based AP simulator for integer-only softmax, modeled SRAM-based AP and 16nm technology, and simulated softmax execution using the data flow modeling I just showed in the previous slide. For the results, for precision sensitivity analysis, this is telling us that for a certain combination of precisions for the softmax kernel, we get an end-to-end perplexity very close to the floating point perplexity. So perplexity is similar to accuracy for DNNs, except that in LLMs it just quantifies a language model's uncertainty. So lower is better. And actually this choice corresponds to this combination of precisions at the different steps of the approximated softmax. And this is fine. We can support different precisions at different levels of the approximation because the AP can support that. And now that we know the optimal mixed precision for the softmax kernel, we take that mixed precision kernel and we approximate accelerating it on the AP. So over here we're showing the AP normalized energy versus the sequence length for different batch sizes for Llama 2 7 billion and 70 billion. And we see that in all cases the ratios are greater than 1, which means the AP is better energy-wise than A100 and RTX 3090. In fact, the average energy savings compared to A100 are up to 300, and the average energy savings compared to 3090 is up to 700. So this is for energy. Now, if you look at the latency, I want you to notice that in some cases for smaller sequence length, the AP is doing a bit worse than A100 and RTX 3090. This is for the reason I mentioned before, that the way we perform the operations is the number of rows is controlled by the sequence length. So at a lower sequence length, we do not have enough parallelism to offset the bit serial operation. But this is not a big problem because we've seen from the characterization that softmax becomes a big deal for larger sequence length. So when the AP is doing better, it has latency savings between 1.06 and 6.7 times compared to A100, and between 1.02 and 12.58 times compared to RTX 3090. Now this is just looking at the softmax kernel, but we can translate this acceleration in the softmax kernel to the overall acceleration in the whole LLM inference. And the way we do this is by relying on Amdahl's law. So assuming everything else is running on the GPU, and we're just doing the softmax kernel on the AP, a 6.7 times softmax speedup, for example, this one. So this is going to be translated into around 10% reduction in the inference execution time, roughly, just relying on Amdahl's law very simplistically. Okay, so we can translate those reductions into end-to-end reductions in the whole LLM model. For comparison with the state-of-the-art, there are two state-of-the-art works, Constmax and Softmax, and the differences compared to us is the way they approximate softmax. So the Constmax uses learnable lookup tables, and Softmax uses base replacement with online normalization. And compared to both, the AP has a better optimum energy per operation. In fact, we have 33 times better optimum energy per operation compared to Consmax, and 117 times better optimum energy per operation compared to Max. Okay, so we hope that this work has shown that APs are viable solutions to accelerate LLMs, or at least a portion of LLMs for now. So in conclusion, so this concludes like my defense. So this is the overall conclusion. APs are capable to accelerate reinforcement learning, CNNs, and LLMs. We've shown that APs offer energy efficiency for different machine learning workload acceleration tasks, and they are flexible to achieve mixed precision inference. We hope that we have been able to say that this equation is viable. So APs do offer acceleration, sustainability, and flexibility, and that we were able to achieve our goal, which is promoting the use of in-memory computing to accelerate machine learning. For our couple of limitations, of course, the scope of simulations. So this has mentioned before. We are relying on analytical models, which is not a very accurate way to estimate things. So this is one limitation. Plus, we are focusing on the AP as a standalone component without like interacting with other components in the system. The other limitation is our models that we studied. So there are other models out there for machine learning, so that we could look onto. For future research directions, we can look into heterogeneous systems, so AP with a CPU, with a GPU, or with another ASIC, and then scale-out systems like chiplets. This could be also something interesting to look at. For our publications, so the first four are the ones I discussed. I just want to mention that I'm still doing research currently, and I'm currently leading 2 works in progress. We're doing end-to-end acceleration of LLMs rather than just a softmax kernel, and we're surveying mixed precision LLMs, and we anticipate we can submit those 2 works by the end of the month. Okay, so that being said, I would like to thank you all for being here. We went a bit over time. I would like to thank my advisor, Professor Fadi, and the committee members, Professor Nickel and Professor Rayner, my mentors at Train and Synopsys, Professor Muhammad and Professor Ruwaida, and my other collaborators in CAUS, in China, and of course at UCI. So thank you, and if you have any questions.
Thank you.
Thank you.
So we have maybe time for some quick questions. Start with the audience, maybe kind of. So, any questions from the audience?
I think they had one. Check the comments.
Yeah, I'm gonna check.
Okay. There was one question.
Let's see. So I think the one for the parallel, I already answered it.
There's one more.
Can the CNN operation be perfectly parallelized only? Then we can do this. The CNN. Oh, I'm not sure to which slide you were mentioning, but the CNN operation can be perfectly parallelized per layer, so layer by layer. Not so in one layer, yes, but we have the sequential part in between layers. Thank you, Rui. Yeah. I think these were the questions in the.
From the committee members, I think. Do you have any further questions?
I can ask one further question that I have. Mariam, you have done a ton of work on a lot of things, all the way from a few bits up to data centers and their huge energy usage and so on. There's a lot of data there and so on. It would help if I would be interested to hear your 2-sentence summary of what is the key contribution here. What's the key lesson learned that you have done in this work? What's the trick to remember? Yes. Something in that direction, which might be something simple or small, but to concentrate something on your contribution in this big work that you have done with all the chapters in your dissertation.
Okay, that's good. So if I want you to remember one thing out of this, it's the following. So we cannot keep squeezing performance out of our traditional architectures. We have to re-look at our hardware architectures, to think in another way, to look at in-memory computing as one viable solution. Because right now, in industry, like in-memory computing is still not a big thing. It's starting to take some traction with some startups, but big companies still rely on the traditional computational architecture. So if there's something I would like to say over here is, maybe it's time to start looking at alternative solutions that are completely different. We can't just keep squeezing performance out of the computational paradigms that we already have out there. And I hope that through this small work that I've done, I've at least motivated part of that. That's my hope. Yeah.
That's a good answer. I like it. Thank you.
Thank you.
Okay, thank you. Any other questions? Good. All right.